So, one of the discoveries of psychology is that the basic unit of the brain appears to be the neuron. The neuron is a specific sort of cell. And a neuron has three major parts, as you could see illustrated here. Neurons actually look quite different from one another, but this is a typical one. There are the dendrites, these little tentacles here. And the dendrites get signals from other neurons. Now these signals can be either excitatory, which is that they raise the likelihood the neuron will fire, or inhibitory, in that they lower the likelihood that the neuron will fire. The cell body sums it up, and you could view it arithmetically. The excitatory signals are pluses, the inhibitory ones are minuses, and then if you get a certain number, plus 60 or something, the neuron will fire. And it fires along the axon, the thing to the right. The axon is much longer than the dendrites. And in fact, some axons are many feet long. There's an axon leading from your spinal cord to your big toe, for instance. It is so shocking the lights go out. To complete a mechanical metaphor that would have led Descartes to despair, thank you, Colleen, surrounding the axon is a myelin sheath, which is actually just insulation. It helps the firing work quicker. So here are some facts about neurons. There are a lot of them, about 1,000 billion of them, and each neuron can be connected to around thousands, perhaps tens of thousands, other neurons. So it's an extraordinarily complicated computing device. Neurons come in three flavors. There are sensory neurons, which take information from the world. So as you see me, for instance, there are neurons firing from your retina, sending signals to your brain. There are motor neurons. If you decide to raise your hand, those are motor neurons telling the muscles what to do. And there are interneurons, which connect the two. And basically, the interneurons do the thinking. They make the connection between sensation and action. It used to be believed, and it's the sort of thing when I taught this course many years ago, I would lecture on, that neurons do not grow back once you lose them. You never get them back. This is actually not true. There are parts of the brain in which neurons can regrow. One interesting thing about neurons is a neuron is like a gun. It either fires or it doesn't. It's all or nothing. If you squeeze the trigger of a gun really hard and really fast, it doesn't fire any faster or harder than if you just squeezed it gently. Now this seems to be strange. How could neurons be all or nothing when sensation is very graded? If somebody next to you pushed on your hand, the degree of pushing, you'd be able to notice it. It's not either pushing or not pushing. You can, degrees of pushing, degrees of heat, degrees of brightness. And the answer is, although neurons are all or nothing, there are ways to code intensity. So one simple way to code intensity is the number of neurons firing. The more neurons, the more intent. Another way to increase intensity is the frequency of firing. So I'll just use those two. The first one is the number of neurons firing. The second one is the frequency of firing. In that something is more intense if it's bang, 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 than bang, bang, bang. And these are two ways through which neurons encode intensity. Now, neurons are connected, and they talk to one another. And it used to be thought they were tied to one another, like a computer. Like you take wires and you connect wires to each other. You wrap them around and connect them. It turns out this isn't the case. It turns out that neurons relate to one another chemically in a kind of interesting way. Between any neurons, between the axon of one neuron and the dendrite of another, there's a tiny gap. The gap could be about 1/10,000th of a millimeter wide, this infinitesimal gap. And this gap is known as a synapse. And what happens is, when a neuron fires, an axon sends chemicals shooting through the gap. These chemicals are known as neurotransmitters. and they affect the dendrites. So neurons communicate to one another chemically. These, again, the chemicals could excite the other neuron, excitatory, bring up the chances it will fire, or inhibit the other neuron, inhibitory. Now, neurotransmitters become interesting because a lot of psychopharmacology, both of the medical sort and the recreational sort, consists of fiddling with neurotransmitters. And so you could see this through some examples. There are two sorts of ways you could fiddle with neurotransmitters, and correspondingly, two sorts of drugs. There are agonists, and what an agonist does is increases the effect of neurotransmitters, either by making more neurotransmitters, or stopping the cleanup of neurotransmitters, or in some cases by faking a neurotransmitter, by mimicking its effects. Then there are antagonists that slow down the amount of neurotransmitters, either because they destroy neurotransmitters, or they make it hard to create more, or in some cases they go to the dendrite of the neuron and they kind of put a paste over it so that the neurotransmitters can't connect. And it's through these clever ways that neurons can affect your mental life. So for instance, there is a drug known as curare. And curare is an antagonist. It's a very particular sort of antagonist. It blocks motor neurons from affecting muscle fibers. What this does then is it paralyzes you, because your motor neurons, you send a command to your arm to lift up, it doesn't work. You send a command to your leg to move, it doesn't work. The motor neurons are deactivated. And then, because the way you breathe is through motor neurons, you then die. There's alcohol. Alcohol is inhibitory. Now, this may be puzzling to people. It's mildly paradoxical, because you may be thinking, alcohol is not inhibitory. On the contrary, when I drink a lot of alcohol, I lose my inhibitions and become a more fun person. I become more aggressive and more sexually vibrant and simply more beautiful. And so, in what way is alcohol inhibitory? Well, the answer is it inhibits the inhibitory parts of your brain. So you have parts of your brain that are basically telling you now, largely in the frontal lobes, sort of, okay, keep your pants on, don't hit anybody, don't use bad words. Alcohol relaxes, shuts down those parts of the brain. If you take enough alcohol, it then goes down to inhibit the excitatory parts of your brain, and then you fall on the floor and pass out. Amphetamines increase the amount of arousal. In particular, they increase the amount of norepinephrine, a neurotransmitter that's responsible for just general arousal. And so amphetamines include drugs like speed and coke. There are Prozac works on serotonin. When we discuss clinical psychology and depression, we'll learn the extent to which neurotransmitter disorders are implicated in certain disorders like depression. And one problem is that for depression is that there's too little of a neurotransmitter known as serotonin. Prozac makes serotonin more prevalent, and so in some extent might help alleviate depression. Parkinson's disease is a disease involving destruction of motor control and loss of motor control, difficulty moving. And one factor in Parkinson's is too little of a neurotransmitter known as dopamine. The drug L-Dopa increases the supply of dopamine, and so does something to alleviate, at least temporarily, the symptoms of Parkinson's. So you have neurons, and they're clustered together, and they fire and they communicate to one another. So how does this all work to give rise to creatures who could do interesting things like talk and think? Well, again, it used to be believed that the brain is wired up like a computer, like a PC or a Mac or something like that. But we know this can't be true. It can't be true because there's two ways in which the brain is better than a computer. For one thing, the brain is highly resistant to damage. If you have a laptop and I persuade you to open it up for me, and I take the pliers and kind of snip just about anywhere, your laptop will be destroyed. But the brain is actually more resilient. You can take a lot of brain damage and still preserve some mental functioning. To some interesting sense, there's some sort of damage resistance built into the brain that allows different parts of the brain to take over if some parts are damaged. A second consideration is the brain is extremely fast. Your computer works on wires and electricity, but your brain uses tissue, and tissue is extremely slow. The paradox then is, how do you create such a fast computer with such slow stuff? And you can't, if the brain was wired up like a personal computer, it would take you 4 hours to recognize a face. But in fact, we could do things extremely quickly. So the question then is, how is the brain wired up? And the answer is, unlike commercially generated computers, the brain works through parallel processing, massively parallel distributed processing. There's a whole lot of research, and this is research, some of which takes place outside psychology departments and in engineering departments and computer science departments, trying to figure out how a computer can do the same things brains can do. And one way people do this is they take a hint from nature and they try to construct massively distributed networks to do aspects of reasoning. So there's a very simple computational network that is interesting because it kind of looks to some extent like the way neurons look, and this is often known as neural networks. And people who study this often claim to be studying neural network modeling, to try to build smart machines by modeling them after brains. And in the last 20 years or so, this has been a huge and vibrant area of study, where people are trying to wire up machines that can do brain-like things from components that look a lot like neurons and are wired up together as neurons are. One consideration in all of this is that this is a very young field and nobody knows how to do it yet. There is no machine yet that can recognize faces or understand sentences at the level of a 2-year-old human. There is no machine yet that can do just about anything people can do in an interesting way. And this is in part because the human brain is wired up in an extraordinarily more complicated way than any sort of simple neural network. This is a sort of schematic diagram, you're not responsible for this, of parts of the visual cortex. And the thing to realize about this is it's extraordinarily simplified. So the brain is a complicated system. Now, so we've talked a little bit about the basic building blocks of the brain, neurons. We've then talked about how neurons can communicate to one another, then turned to how neurons are wired up